get your last snacks. Welcome, everyone. I hope you're having a great time at Climate Day at the Wonder House and learning a lot of great things. So I'm Carmi Garzione, and I'm the Dean of the College of Science, and I'm very pleased to introduce our next speaker, Dr. Laura Condon. Dr. Condon is an associate professor in the Department of Hydrology and Atmospheric Sciences at the University of Arizona, where her research focuses on water, sustainability, and climate. Dr. Condon is interested in large-scale water sustainability and the dynamic behavior of managed hydrologic water systems in the context of past development and future climate change. Her work combines physically based numerical models with observations and statistical techniques to evaluate integrated natural and human-managed water systems. In addition to her academic experience, Dr. Condon has worked as an engineer, consultant, and as a hydrologist for the Bureau of Reclamation, where she worked on water resources management issues in Colorado and across the western United States. So understanding and predicting watershed behaviors, both in a changing climate and with changing human needs, is a big challenge, especially when you are adding the changes that we make to move water around for human habitation and agriculture. So big data with simple front-end tools can help city planners and water managers start to make smart choices about decisions that have lasting ramifications on people's lives. And today, Laura is going to help us understand how she can figure out what your water did last summer. Welcome, Laura.
I'll just start off and say that that's a tough act to follow from the last talk, and it's only me up here, but I'll do the best I can. So yeah, I'd like to start by asking you a question. Do you know what your watershed did last summer? Because I do, and I think we should talk about it. I also need a clicker. Do I have a clicker? All right, well, we'll just wait a second. Oh, thank you. Okay, now we're off and running for real. Okay, so I do know what it did, and I want to talk about it, and I should warn you before I get going that this is going to be a talk about water sustainability. And I know the minute I say that all sorts of negative headlines are flashing across your mind. Of course, the western U.S. is in the worst drought in over 1,000 years. We have flooding occurring. You heard a lot about that with the last talk. We worry about aquifers running out of water. We've had some of the worst fire seasons. There's all sorts of bad news to go around. And I could spend my time talking about any of these, but actually what I want to talk about today is the story behind the story, and that is watersheds. We rely on built systems to get waters to our taps, canals, reservoirs, pipelines, water treatment plants. But what I'd like to convince you of today is that watersheds are really the start and the end of this story. They're already doing most of the work in our systems, and they're going to continue doing most of the work. So it's really important that we understand them if we're going to be able to manage for the future. So to start off, I'd like to ask you to think back to the last time that it was raining, wherever you were. And remember what you were doing during that rainstorm. Now imagine, instead of doing whatever you were doing, you got a cup and you went and you stood outside for the entire rainstorm. How much water do you think you would have collected in your cup? So if you had kind of an average size cup and it rained an inch, that would have been a really good rainstorm. You would have collected about 4 ounces of water. That's basically a small serving of wine. So next question, how long ago was that rainstorm? And this is a really important question because if the water you collected in your cup is the only water you've had to drink, how many of us would still be here today after that rainstorm? Probably not too many, right? Because we need about 2 liters of water a day to survive, and we can't make it more than a couple days without water. Okay, so maybe I'll build a bigger cup, right? So I live in Tucson. We get about 1 foot of rain per year. So if I wanted to collect enough water just to survive, I would need a cup that's about 25 square feet. This is what 25 square feet looks like. Unfortunately, though, that's just enough water to survive. So if I want to take a shower, do all the things, cooking that we normally do, we actually use more like 300 liters of water a day. If I want to collect 300 liters of water a day, I need an area about 3,000 square feet, about the size of the patio outside. For reference, the average home in the US is about 2,400 square feet. And I want to remind you that that's just me, right? So if there are, say, 30 of us in this room, all of a sudden now we need 40,000 square feet. And you might say, okay, Tucson's really dry, you get no rain. If we're in Austin, you get about 3 times the amount of rain, about 3 feet of rain a year. But we still need a really large area. So what would happen if we thought about the whole world this way? What if we were all just dots on the map, right? You can take this to its logical conclusion pretty easily and see that that's not going to work out very well. Of course, this analogy doesn't really make a lot of sense, though, right? Because what's missing in this analogy is the idea of connection. And what's really beautiful about our natural systems is that they are networks. So these are the rivers of the United States that form the watersheds. And the watersheds are what's providing the water for you to drink. We are not isolated dots. You have this incredible system working for you and providing the water supplies that we depend on. And that's what I want to talk about today. So I keep saying the word watershed. What do I mean by that? If you drop your finger anywhere on the map, we can trace out a watershed. And basically, within the watershed, anywhere that a raindrop falls, it will eventually make its way to the outlet of this watershed. Pretty cool. This is really, truly just the tip of the iceberg, though, when we think about our river networks. So you might think back to the water cycle as you learned it in elementary school. Rain falls on the ground, goes into the rivers, flows to the ocean, evaporates again. We go around in a big circle. But this is really just part of the story. And to illustrate that point, I want you to think about what it actually looks like when it rains. This is what it looks like on a paved surface where you might see water just flowing over the ground. But this is not something you actually see in a natural landscape. When's the last time you were standing on a natural hill slope and saw sheets of water running down at you? This isn't actually how it works in our systems. So if we think about a system more like this, a natural landscape, what happens when it rains? Where does the water go? To do that, we'll go back to school just for a few minutes. So there's a lot of processes that we could talk about here. But in general, rain falls, some of that water runs off into the river, but a lot of the water actually works its way underground. And some of it, it will be then stored in the pore spaces underground. We'll talk about that more in a minute. If it makes it all the way down here, this is called the water table. That's where all of the pores are filled with water. And below that is what we call groundwater. And groundwater is really, really important to our story, and it's something that a lot of people don't really understand. So we're going to take a few minutes to talk about what groundwater is and why it matters to you. When I say groundwater, the first image that might come to your mind is a prehistoric river or a flooded cave, something really cool like this that you could scuba dive through. And it's true, these are real pictures. There are karst systems that look like this. But this is really not what most of the groundwater is that we're talking about. Most of the groundwater we're talking about is a lot less sexy. It's water in a hole, right? But it's really, really important. Why do we care about this water? How did it get there? Where's it going? This is actually really important if we want to understand how our watersheds behave. And I want to illustrate a couple of things to understand about this. First of all, I want to point out that the water can infiltrate everywhere. Wherever you are on the planet, unless you're standing on top of an active volcano, if you start digging down, eventually you will find water. Groundwater is everywhere. And it's not just standing still, it's moving around. Gravity applies underground too. And this leads to some really important characteristics. So what you can see here, we have variable depth of our water table. And what this means is that on the where groundwater is converging around our streams, we have really shallow groundwater, and plants can access this water with their roots. That means that they have a really stable water supply, and they're not just dependent on the water when it rains. This is why, if you look at a landscape, you might see different plants occurring near our rivers, because they have access to groundwater. The connections to rivers are really important too. You can see here in my drawing that the groundwater is actually touching our stream. And this is really important because that means that our groundwater can be flowing into our streams. This is what we call base flow. And if you think about something like the Colorado River, a really important surface water body, actually more than 50% of the flow in the Colorado River is base flow by the time it reaches the lower basin. Base flow is the water that comes from the groundwater. So if you want to predict stream flow, especially if you want to predict stream flow in a drought, you need to know what the groundwater is doing. Again, the groundwater is really important because it moves really slowly. It's this slow, stabilizing buffer to our system. And if our groundwater gets lower, we will impact our stream flows. And that's a story that we're seeing play out right now. I talked a lot about rain, what happens if it snows. The story is really pretty similar. You can think about our conceptual model. When the snow melts, all of the same rules apply. We're still following gravity. A lot of water is going to infiltrate, work its way to streams. What's really important about snow, though, is that it's a natural reservoir. We don't have to do anything. The snow stays in the mountains in the winter and then melts and runs off in the spring and summer when we want to use it. That is super convenient. So, okay, watersheds, really cool. Maybe you learned some things you didn't know. Why am I telling you this? I want to go back to the first point I made about watersheds really being the start and end of this story. So I'd like to put this in perspective. Surface water, our fresh surface water, is about, streams are about 1% of our total fresh water available on the planet. Groundwater is 99%. So on this screen, this line is taking up 1% of the space. That might seem crazy to you, that it's such a small number, but actually if you've flown in an airplane, it makes sense. If you look out your window and look at the landscape, you'll realize that the rivers are actually pretty small features. These are 1%. Everywhere else on the landscape, water is infiltrating and groundwater is everywhere. You can also think about our major built systems. So this is Glen Canyon Dam. And it creates Lake Powell, which is the second largest reservoir in the United States, almost 200 miles long when it's full. It is far from full right now, but a really, really huge system, right? Now if we zoom out and think about that in the context of the landscape, Lake Powell is actually the lower point of the upper Colorado River Basin. You can see it's still small. It's small in comparison to our total landscape. I'm going to make this point just one more way, and then I'll let it go. But so if we take all of the surface water in our streams and lakes, and we imagine that that's a Red Bull, so it's about 8 ounces, then relative to that, all of the water in the snow, not the glaciers, but the snow that melts every year, would be about a 12-ounce can of beer. And if you think about all of the water that we could possibly store in all of our human structures, if they were full, which they are not, that would be about 2 bottles of wine. So we've got enough drinks here for about 10 people. If you invite them all over and you have a big enough hot tub, then the water in the hot tub is the groundwater. And literally all of the surface water that we have is the drink in your hand. And it's not just a story about storage. Watersheds are also moving water for free. The Colorado River is about 1,400 miles long. It transports that water. We don't have to do anything. For reference, the Central Arizona Project is a really critical piece of infrastructure. It takes water from the Colorado River to Central Arizona, places like Phoenix and Tucson, where we live. That took about 20 years and billions of dollars to build, and takes a huge amount of energy to operate every year. Rivers are doing this for free. So this all seems like good news, right? We have these watersheds. They're doing great work. Turns out they do it for free. They do it while we're sleeping. There's all this groundwater you weren't even thinking about. We're in great shape. So what's the problem? Well, the problem is that this is a real picture of Lake Mead, and this isn't even the most recent picture of Lake Mead. It looks even worse if you took a picture today. And we're experiencing a horrible drought. We are really running out of water on the Colorado River. It's in crisis. So why is that happening? It's happening because, not just because we're not getting enough snow, but actually because we're fundamentally changing the landscapes. We have changed not just infrastructure, how we divert and use water, but all of our built landscapes change the way that water infiltrates and runs off in our systems. So when we see something like this, Lake Powell going dry, it's not just a question of how much precipitation we got. This is really an indication of a watershed that's changing. Just to put that in reference, 2021 and 2022, we had actually roughly average snowpack. Those weren't horrible snowpack years, but for that same snowpack, we only got 1/3 to 2/3 of our normal runoff. The reason why that's happening is because the system is warming and drying, so we're getting less water out of the same amount of snow. That's a really big problem, and that's a problem that is going to continue into the future, so we have to take it really seriously. You can think back to the conceptual models I showed you earlier. When we have a warmer system, plants are going to use more water. And if we start drying out our system and lowering our water table, water that was flowing into our streams, we could actually have the opposite happening. We call this losing streams, where now water is actually flowing from our streams back into the groundwater. If you want an analogy, you can just think about holding a sponge under a faucet. So if you have a sponge that's wet and you hold it under a faucet, a lot of water is going to run off. If you have a sponge that's dry, before that water can run off, it's going to soak up and wet the sponge, right? So as we're drying out our watersheds, we're changing the way that they're going to respond to the weather. I've told this story from the perspective of the Colorado River, but it's really a problem that's happening across the western US as we expect to see increasing aridification moving eastward across the country. Climate change is one story. There are other stories that we can tell about the way we change our watersheds. Agriculture is another great story to tell. We rely on agriculture, of course, to provide all of the food we need, but a lot of our agriculture is groundwater dependent. And what that means is if we're pumping groundwater and we pump the groundwater at a rate faster than it's able to recharge, then our water tables are going to lower. So we're just sticking a lot of straws into the ground, and we are collectively lowering the water table. And in addition to pulling out water that we might need for the future if we're withdrawing it in an unsustainable way, we're also going to impact our streams, as I've already talked to you about. So a good example of this is actually Tucson. Tucson has one of the longest histories of cultivated agriculture in the entire US along the banks of the Santa Cruz River. However, the Santa Cruz River died decades ago, not because we diverted all of the surface water, but actually because as the city of Tucson grew up, we pumped more groundwater and lowered the water table to the point where there was no longer this connection to provide flow to the river in between rainy periods. So today, except in actively managed areas, this is what the Santa Cruz River looks like. We completely lost our surface water body, not because the rain stopped, but because we changed what was happening underground. Similarly, with our landscape management practices, both with respect to forest management and climate change, we've had some of the worst fire seasons in decades. When we have fires in forests, that changes the soil, and it actually makes it harder for water to infiltrate. So again, if we get the same rainstorm, but on a burnt environment, we will get more runoff, we can get dangerous debris flows, and those can have impacts really far downstream from where the fire occurred. And if, hypothetically, you are in California, where we have atmospheric river events occurring, following on a lot of really bad fire seasons, this can be really problematic. This is just another example of a situation where the watershed itself has actually changed. So not only do we need to worry about what's happening with the weather and what the inputs are, if we want to predict what the watershed is going to do, we have to understand these much more complex interactions. And this goes back to a really fundamental problem of our future not really looking like our past anymore. We have a lot of uncertainty, and we expect that the future is going to fall outside the bounds of what we've seen in the past. And this is really a big challenge to predict. So how do we fix this? So as a scientist, I spend a lot of my time trying to figure out how to fix this. And I think about all of the complicated interactions that I've been talking about. So the connections between plants and recharge, connections between groundwater and surface water, connections between our human decision-making and the amount of water we pull out of the environment. This is all really complex, and it's also really hard to observe because a lot of the processes I care about are happening underground, and we have a limited number of groundwater wells that we can use to observe that. And really, what I want to do is be able to understand the full water and energy balance across the entire landscape. Because if we can't rely on the fact that the relationships that we observed in the past are going to stay the same, for example, the amount of snow translating to the same amount of stream flow, then we actually really have to simulate the system in a pretty comprehensive way if we want to make a good prediction. So what I do is do this with computer models, where we can simulate all of these interactions, and we can also play what-if games about what will happen in the future. So you can think about taking this really complicated landscape and the equations that have been established for how water and energy move within these systems, and I put those into models where basically every piece of my landscape becomes one grid cell in my model. And then across my model, I have to solve those equations everywhere. Our team at U of A, in collaboration with other scientists across the country, has helped build the first national model that actually fully resolves groundwater flow across the United States at 1 kilometer resolution. This is really fun. We can ask a lot of science questions with this model. It's also a really big computational problem because we have about 8 million grid cells in this model. Every grid cell is a cell where we have to solve all of these equations. And we end up running these on really large supercomputers to be able to do simulations and figure out what's going to happen in the future. We can learn a lot from this. So we've done a lot of science. I've led papers to look at how groundwater connections are changing our systems, how deep we need to be thinking, and how human decision-making around groundwater can actually change the dynamics of watersheds. There's a lot more we can do on this, and this is really exciting work. But I'd also like to point out that this is not enough. Our physics-based models are the most rigorous models that we have, but they are really expensive to build. They're expensive to run, and as a result, they're really not well suited to operational challenges where we need answers fast, and we need to be able to run things repeatedly to understand ensembles and risk. So we've taken this work, and we're now building a project called Hydrogen, where we are developing machine learning models so that we can get the answers faster, still taking advantage of our really rigorous physics-based models. So to do that, we start with our physics-based model, then we build machine learning emulators on top of that. Our machine learning emulators can basically mimic our physically based models, but we can speed up our simulations by about 1,000 times. And what's really powerful about our approach is because we're able to train on simulations in addition to data, we can really start to use them to explore systems that we haven't observed in the past, where relationships might be changing, and also to simulate systems where groundwater is really important, and that's a system we have a really hard time observing. So our approach is better for understanding extreme events, again, things we haven't seen in the past. We can also do a really good job of simulating things that fall on long time scales, so thinking outside kind of the time scale of your typical weather forecast, about 2 weeks, thinking out months in advance. That's where groundwater and the really slow-moving parts of our systems are critically important if you want to understand what's going to happen. In addition, because we can train on our physically based models, we can look at the entire watershed, not just thinking about the stream flow that we can see, but all of the processes that are supporting that. And with this project, we're really focused on building tools that are operational and are usable to a large group of people. So we think about water resources managers who have to make decisions about how they're going to build and plan infrastructure, farmers who need to decide whether to fallow land, and insurance groups that have to make decisions about the large risks that they're facing. This is just a snapshot of what our platform looks like. This is just a snapshot of what our platform looks like. We have a web-based platform, so we're not requiring people to come in with any knowledge of how to build or run a hydrologic model. And with our platform, you can do several things. You can define watersheds and generate your own forecasts on demand. You can explore current conditions, thinking about things like soil moisture and water table depth, things that most of our current products don't include because they're really hard to simulate. And you can also explore all of the national observations, all of the national point observations around watersheds in one place. So we're continuing working on this. There's a lot of science still to do. But what I'd like to leave you with is to go back to the original question, because actually, even though there's a lot we don't understand, we know the end of this story. We know what your watershed did last summer. It's the same thing it's going to do this summer, and hopefully for many summers to come. Our watersheds right now are balancing water and energy for us. We have snow that is being stored in the mountains, groundwater underneath our feet everywhere we are, and we have rivers and watersheds that are transporting water where we need it for free. So what can we do? I mentioned that it's really important that we understand and appreciate our watershed systems. So the first thing you can do is find out about your watershed and where your water comes from, and what are the policies that are enacted to manage water where you live. You can advocate for better policies if you find instances, which there are many, in which policies are not well aligned with the health of our watersheds and the sustainability of our watersheds. No matter where you are, you can conserve water because it's always a precious resource, especially clean, fresh water. We need to be really careful with it. And you can support infiltration. Hopefully I've convinced you how important groundwater is. It's really important that we don't contaminate our groundwater and that we have water infiltrating into the subsurface, because that is what is buffering our entire systems. So in conclusion, I'd just like you to remember that you are not a dot, you're not just a cup, and thank goodness you're not, because we're a network, and the network, our watershed networks, are supporting us. Everything that you do will impact people downstream from you, and you are dependent on everything that's happened upstream from you. The water that you're going to drink next week, even next year, a lot of that water is already in our systems, working its way to you. And I hope that's something that you'll remember the next time that it rains. Questions?
How many can I ask?
You can start with one. We can go from there.
I come from Australia.
Mm-hmm.
I work in West Sydney Water.
Mm-hmm.
I'm mapping our work there, and I'm also working in the Murray-Darling Basin as well.
Mm-hmm.
So I work on
So you know about drought?
a little bit.
Yeah.
We're trying to do 1 metre data.
You're trying to do what?
1 metre data. You mentioned
Okay. Yep.
K data, so that's one thing. Are you going higher resolution?
We can run models at higher resolution. So the physically based models I talked about, we can actually run all the way down to the pore scale if we wanted to with the equations we're solving. Our limitation is really data. So at the national scale, we want it run at 1 kilometer where we have data sets to support it. But on smaller scales, we can definitely run at higher resolution.
Just one other one I'm thinking of. Are you thinking about decentralised models for doing this as well as, are you doing centralised?
What do you mean by decentralized? Decentralized?
I'm an adjunct professor at 6 universities, so we're sharing resources. So it helps. You mentioned.
Oh, yeah. So absolutely, yeah. We run all of our simulations on large research-based clouds, and all of our data we share and we publish, and we have our platform for sharing our results openly. Yeah. Thanks.
So I'm going to send you an email. That's all. Just
Great. Yeah.
keep touching base.
I'm sorry. In my neighborhood, a lot of rainwater lands in the street. It goes down the street. It goes into the stormwater system, and I never see it again. Does any of that? This is in Tucson, Arizona. Does any of that get ultimately captured and going back into recharge, or does it? What happens to it after I lose sight of it?
Sure. So there's a lot of variables that depend. I'm not familiar with your particular neighborhood, but if the rain falls really hard, as it tends to do in Tucson, the rain can fall harder than it can than the rate that it can infiltrate. So we actually have, a lot of times in Tucson, we have rain that happens really fast. It comes through, and most of that water actually runs off and makes it very far downstream before it's infiltrating. That's what a lot of stormwater retention programs are about, is trying to slow down the water, have more water infiltrate where we are, versus getting these really large storm surges, which are problematic both for driving down the street, and also means we're not getting nearly as much recharge locally.
Thanks for the talk. That was great. I was just wondering to what degree the ocean water and sea temperatures and everything that's happening out in the oceans affects how you predict what's going to happen over land.
Absolutely. I'll just hand that over to Joellen. It matters a lot. So in our models, what we are kind of the top boundary condition of our model is the weather. So we say, if it rains, what's going to happen? If it snows, what's going to happen? Where's that going to go? But we rely on the results of other models that are simulating the oceans and the atmosphere to generate predictions for us of, okay, how much rain is going to happen here that we can then simulate. We're really focused on how the watershed is going to respond. Yes?
So you mentioned that a lot of the water that goes back to the rivers actually comes from the groundwater, and that some of the plants will take up that water and then transpire it. So, for instance, in Tucson, we have I think it's the Million Tree planting initiative, and to increase trees to combat climate change. But is that going to dry up all our water?
Good question. So it really depends how you're providing water for those trees, actually, because I would think in Tucson, what you're going to end up doing is irrigating those trees so that they don't die in the first summer you plant them. And actually, in places where we're irrigating, we get a bunch of groundwater recharge because we generally apply more water than the plants actually use. So I think it would probably be a net positive in terms of recharge.
What's next? What's your next big project?
Right now, we're really focused on machine learning and being able to run watershed simulations operationally out seasonally and annually for people who are not scientists, because it takes so much work and effort and time to build these really large, complex, physically based models. And the problem is that we just need answers much faster than that. That's exactly what you and Beth were talking about, right? Like, we got to get answers faster than that. And so we're working on models that can run fast and give accurate answers quickly. Good. Thank you. Oh, one more. Sorry.
Hey, thank you for your time today. I was wondering if there's anything we can learn from the research and practice of your machine learning and analysis that could apply to the events that happened in Ohio with Norfolk Southern to help clean out the water that's been really polluted for everyone who's drinking it there? What can we take from this that maybe you're aware of as research that's already going on, or kind of what that call to action might look like?
Absolutely. So all of the models that I was talking about are focused on water quantity, not water quality. However, you can couple with the types of simulations I'm doing, hydrogeochemical models, and you can couple particle tracking models to try to understand if you have pollution to the groundwater, exactly where it's going to go and what you would need to do to contain it. So there's a lot we can do with modeling to better understand and predict the human health risks that we would be seeing. Oh.
I'm wondering, can this modeling be scaled down to the level of a building or like a city block or a part of a city plan to help come up with best practices for that particular instance for maintaining the change in stormwater retention, or to make sure that the new development that is being planned would not be a net negative on the water table?
Yeah, so the answer to that would be yes and no. So absolutely, we can scale it down, and you could do local simulations of just what's happening with how much recharge you have versus how much water would be taken up, and you could answer the question that you're asking about whether you're a net positive or a net negative. In general, though, you would also want to think about, if you're doing something like citywide planning, you would want to think about how the larger watershed that you're a part of is behaving. So you would want to consider that local interaction, but then also, as I was mentioning earlier in my talk, with the groundwater not just staying there, right? Like, it's flowing. And so you want to understand where you have groundwater converging and where it's going and what your impact is on a larger scale. So yes, and in addition, you would want to do some large-scale modeling.
Thank you for your time. I noticed you ran a map earlier of the Santa Catalinas tracing the water coming down after our recent fires. I live in the neighborhood where that stream comes out, and several of my neighbors have been washed out of their homes. Is there any silver lining to the fires in the mountains that will collect more groundwater in the basin now?
There's not really a groundwater silver lining to that, because the issue is that water is really running off really fast, so we're not infiltrating that water. Yeah, there's not a lot of infiltration happening as a result of that, unfortunately.
And do you think the catchment works that they're doing in the Rito River are effective?
They seem to be. I'm not an expert in those projects specifically, but I have observed them, and absolutely where we can increase the amount of water we're putting back into the system, especially when it's not in a flash flood situation where that water has time to infiltrate, we can actually bring back rivers for sure.
Thank you.
Oh, there's one more.
Oh, thank you. Great talk. So, what tools do you use to help you calibrate your models, or to understand, whether you're accurately capturing some of these natural processes?
Yeah, it's really a big data challenge. So we look at, obviously, all the groundwater observations that we have access to, groundwater wells. We can look at large-scale, like GRACE satellite data, but that's at such a low resolution, it's honestly not as helpful for us. But actually, we pay a lot of attention to how well we're doing at simulating stream flow, because within our models, we don't say a priori, like, this is a stream, this is what the stream should do. The streams actually form as a function of where water is converging, so they can appear and disappear in our model. So when we compare to stream flow, we can actually understand a lot about how we're doing in our groundwater simulations, too. So we just basically grab all of the observations of every variable we can to try to understand how we're doing. All right, I think that is all the questions now. Yep, okay, thank you.